Okay, folks, what we're looking at today is actually how to get the most out of the graphing calculator and actually use it to solve projectile problems. Now, it turns out for level to level, I'm going to say up front, you'll probably find it easier to use algebraic solutions using symmetry than using a calculator to do this. But it could actually prove to be faster in solving several things at once. Now, I'll show you what I mean, but first we have to talk about what our problem is going to be. For example, now this particular example, we have an object that we don't know the range of, and we don't know how high it will go. We do know the vertical displacement is 0 because it's level to level, but let's ignore that for now because we could use symmetry if we knew that. We have a 49-degree angle and an initial velocity of 35 meters per second, and we don't know the time. We know that this thing is launched on Earth, so therefore it has an acceleration of gravity of a downward 10 meters per second squared, or 9.8 if you want to be a little more, I guess, precise. But what do we do with this information if we want to use the calculator? Well, it starts with the equation for the position in the y direction. Y equals y naught plus the initial velocity in the y direction, v naught sine theta, times t minus 1/2 gt squared. Now, a reminder, the g does not have to be negative because it's already a minus in the front. Now, what we're going to do is we're going to plug the information that was provided in the problem. Now, typically I'd say don't do this because you should do algebra first. But in this case, you're definitely doing it. And the reason we're doing that is we're going to actually include the 0 because we launched it from the ground. We're going to include the 35 meters per second times the sine of 49. And then you have t minus 5 because half of 10. We're using the 10. And then we get t squared. Now what I'm going to do is I'm actually going to turn this into an equation that's going to be a little more easy to put into a calculator. One with y's and x's instead of y's and t's. Now, the next step is using the calculator. So to that end, let's turn it on and do a few things right at the beginning. What we'd like to do first of all is check to make sure that we are in fact degrees, not radians, because our problem gave us degrees. So we want to make sure we're in degrees. So once you found the mode, you can get out of that, and now we can actually proceed with the next part. The next part is graphing this. So to do that, we go to the y equals button, and you wind up with a plot showing up, and we're just going to plug this in as we see it. Now we're not going to put the 0, that makes sense. 35 sine of 49 degrees, close parentheses, x. Now it's important you close that parentheses. If you don't, it's going to do something weird with the 49 and the x. Next, minus 5x squared. Now that's this equation. So all we have to do is hit the graph button. And what's happening on the screen right now is we're actually graphing the plot. Now, at this point, it doesn't show the full graph. And it's kind of showing me a couple things. First of all, it's 0, 0, and x is 0, y is 0, so that makes sense. If this is 0 and that's 0, then the whole thing goes to being 0, so y is 0. Then it has another place where y equals 0. That's going to be interesting to us later. That means where this is equal to 0. That's the time, because remember x is time. That's the time in which it lands. But first, let's actually get the whole thing to where we can see it. To that, we got a couple of options. We could adjust our window. So we can go to Window and make adjustments there. We could also go to Zoom. Now, one option is, if you don't have it in a standard window, is to hit 6. Now, you could also hit something called Zoom 0 or Zoom Fit. We'll see if we'll try that and see what happens. Now, look what it did. It gave us a whole lot of negative stuff. I mean, we got all this negative information and only a tiny sliver of that positive part. Well, we're going to hit another zoom. And this zoom is going to be zoom box. And the reason why we're going to hit zoom box is because with our cursor, we can move it all the way up. It's kind of hard to see, but I'm actually moving this up. And what you want to do is get the top of the screen and hit enter. Now what the box will do is as you move over, it actually is making a boxed window so you can actually see what's going on. So I'll move that down and I should have the whole thing in that window. Let's see. Almost. I've got a little bit still missing. So I'm going to be really annoying and make sure I have everything in there. So this will be turned to 0 on the window. I hit that window button. And I'll make the height just a bit taller. We'll call it 40. or 44. 40 is good. And now what I'm looking at is the full window of the projectile's path. And it turns out this is actually a picture of the flight of the projectile. Now, if I would like to find the maximum height, then with this information, I could just go to second trace or calc, and I could go to 4. And what you want to do is you want to find to the left of the maximum. So find a point to the left, enter. Find a point to the right, enter. Find a point that you think is going to be the maximum height. I always cheat and just go a little bit to the left of the right one. And let it do its job. And what it just told us is our maximum height that the projectile achieves is 34.887176. Well, for our purposes, we'll call it 35. That's the maximum height. Now, the maximum time, or the time it took to reach that height, is the x value. So it's around 2.6 seconds. That's how long it took the object to get to the very top. Now, if I'd like to know how long it takes to get right here, well, that is actually something called a 0. So I can go down here, hit 0. I want not that 0, I want that 0. So again, I've got to do the left bound, and it just has to be left of the place I'm interested in. So that'll work. And then I want to do the right bound. So I've got to go all the way past this. It takes a while. And past. And I got to guess, which basically means a little bit to the left or right. And there it tells me that's when my y position is 0, my x is 5.3 seconds. Now, basically, with graphing, I was able to solve for the maximum height, the time it takes the maximum height, and I was also able to find the time it took to reach the ground again. And I could actually use that time with the velocity in the x direction and the angle, so v naught cosine theta, I could then multiply that to that time and I could find the maximum range. Now, where using a calculator is really useful is when you have a displacement that is not 0, which means you have a difference between where you start and you finish in your y direction. This calculator can actually allow you to solve for all the same information. You can find out maximum height, you can find out how long it takes to hit the ground, even if you're starting from a cliff. So, using these methods of using a graphing calculator are very essential to solving more difficult projectile problems. They're not expected to be used whenever you have symmetry at your advantage, but it also sometimes can be a very quick thing. You found 3 pieces of information and easily find a third. There's also a thing you could do where you can graph the range equation, and you could also quickly find out what the range is also. But that's a little bit beyond what we're going to be doing with this particular video. So that's how you use a graphing calculator to try to get the most information about a projectile's path. Okay, so next time we're going to be looking at some special equations for level-to-level projectiles only, and so therefore keep that in mind, and I'll talk to you later.